Yes, welcome you back to my channel, and today we are going to look at energy level diagrams and Born-Haber cycles, and we are going to realize that all these help us get the lattice energies. For example, this energy level diagram can help us get the lattice energies, electron affinities, enthalpies of formation, etc. And for the Born-Haber cycle, we can as well get bond energies using Born-Haber cycle. So our first diagram that we shall look at is what we call the energy level diagram. We are going to first look at those ones involving the energy level diagrams and how we draw. All of them can give you the same answers, but we need to always be specific on what is needed to be drawn. Yeah, so basically, we are going to begin with the energy level diagram, and the energy level diagram simply shows the energy changes in the order they happen. So here we shall make sure that if the energy diagram is positive, rather if the enthalpy is positive, we must be showing our arrow upwards. If it is negative, we'll show the arrow downwards. For example, as you can see, all these energies, it is enthalpy of formation and electron affinity that are negative. So those energies will be shown facing downwards. You need to know that endothermic, as I've told you, endothermic or positive enthalpy changes are shown upwards, while the exothermic or negative energy changes are shown downwards. And this diagram also must have well-balanced equations for the reactions taking place, and you must write correct symbols inclusive. The energy changes should be labeled. So it is something that is time consuming, but very easy. Actually, it is not even time consuming, provided practice. Also, we need to be knowing the meaning of the terms like enthalpy of formation, enthalpy of atomization, bond dissociation energy, ionization energy, electron affinity. So for example, when you talk about enthalpy of formation, if I'm to remind you from our first video, enthalpy of formation of a compound is the heat that is evolved or absorbed when 1 mole of a compound is formed from its constituent elements in their normal states. So the energy that is given out, or the energy that is absorbed when 1 mole of a substance or a compound is formed from its constituent elements in their normal states, is what we call the enthalpy of formation. Then we've also gotten what we call atomization energy. As you can see here, we are having atomization energy. So when we talk about atomization energy, we are meaning the heat that is absorbed when an element in its normal physical state is converted to 1 mole of free gaseous atoms. Yeah, so if they give it to you as standard enthalpy of atomization, you have to add at 1 atmosphere and 298 kelvins. Yeah, so but basically, as I've told you, atomization energy, that is when 1 mole of an element is in its normal state is converted to its free gaseous atoms. Yeah, and we shall also look at enthalpy of sublimation. Is it somewhere? Enthalpy of sublimation? No, much as it is not included somewhere, but we need to really know what enthalpy of sublimation is. Enthalpy of sublimation is the heat absorbed when 1 mole of an element in its solid state is converted to 1 mole of free gaseous atoms. So it's related to atomization. When we convert a substance in its normal physical state to the free gaseous atom, we say that that heat evolved is what we call, rather the heat absorbed is what we call sublimation energy, or heat of sublimation, or standard enthalpy of sublimation. Then when we talk about bond dissociation energy, This is in our third video, but we need to first know what bond energy is. When we talk about bond energy, that is the heat given out when 1 mole of a single covalent bond of a diatomic molecule is formed from its free gaseous atoms. When we form 1 mole of a diatomic molecule, if I have, for example, hydrogen, and I form hydrogen molecule, we are going to find out that the heat that is absorbed, the heat that is given out, because here we are forming a bond, so heat has to be given out. So the heat that is given out when 1 mole of a single covalent bond of a diatomic molecule is formed from gaseous atoms, free gaseous atoms, that is what we call the bond energy. Then when we say bond dissociation energy, now we have bond dissociation energy. That molecule formed maybe breaking, it formed 2 hydrogen atoms. So when we say bond dissociation energy, that is the energy required to break 1 mole of a single covalent bond of a diatomic molecule to form free gaseous atoms. So here we are breaking 1 mole of a single diatomic molecule to form free gaseous atoms. Then when we talk about ionization energy, because we are going to be looking at metals undergoing ionization energy or being converted to positively charged gaseous atoms. So when we say ionization energy, that is the minimum amount of energy required to remove an electron from a gaseous atom to form a charged gaseous ion. For example, if I have substance X gaseous atom and it is forming a positive gaseous ion plus electron, so what the energy that is evolved here is what we call the ionization energy. So basically, when we say, like, for example, the first ionization energy, as you can see here, the first ionization energy will be defined as the minimum amount of energy required to remove an electron from a gaseous atom to form a unipositively charged gaseous ion. We are going to be looking at it when we are really drawing those energy level diagrams. Then when we talk about electron affinity, there a gaseous atom gains an electron to form a negatively charged gaseous ion. So when we're defining ionization, electron affinity, it refers to the energy given out when 1 mole of electrons combines with 1 mole of gaseous atoms to form 1 mole of negatively charged gaseous ions. Yeah. So we are going to look at how to apply all these energy changes to draw the energy level diagrams. Well, the question goes, we are given these. We are given standard enthalpy of formation, enthalpy of atomization, bond dissociation energy, first ionization energy, second ionization energy, third ionization energy, and a first electron affinity of fluorine. They want us to draw the energy level diagram for the formation of aluminum fluoride. Note that the enthalpy of formation is negative. So we shall form it. Since it is given as negative, we shall really show it as negative. So let's see how we draw this diagram, and then we answer the rest of the questions. Hope you had coped it. Hope you had coped the question. That's why I first went through the terms so that one B is copying it. Okay, so well, when we are drawing the energy level diagram, you must make sure that the symbols are shown and should be correct. The chemical symbols must be correct. The state symbols must be correct. The ions should have correct charges. The cycle should have well-balanced equations. And the enthalpy value should be shown along with the reactions they represent in the cycle. And for the energy level diagram that we are going to draw, it is quite important to consider the ranges between any two energy terms. So basically, I'm going to draw I have this. Give it a heading to be smart. energy level diagram for the formation of aluminum fluoride. So since we have enthalpy of formation as a negative value, we can have something like this. Maybe here I have a 0, but my enthalpy of formation of aluminum fluoride is negative. Here we shall have potential energy in kilojoules per mole. So now the first one is the enthalpy of formation we have enthalpy of formation of aluminum fluoride. So here, since it is negative, the first value was enthalpy of formation of aluminum fluoride, and it is negative. So allow me to show it as the HF as -1301. Yeah, and here we are forming aluminum fluoride solid. Now, then we have enthalpy of atomization of aluminum. That is when 1 mole of aluminum is converted to the gaseous atom. So we are going to have the equation. We have aluminum here. We have aluminum solid plus, since aluminum fluoride is F3, so we shall add 3 out of 2 fluorine gas. But remember, here, this aluminum solid, here we shall have enthalpy of atomization. Let me call it the HA, and it is positive 314. So at this rate, it has been converted to a gas. So now aluminum is going to be used as a gas. So our second equation will be aluminum as a gas plus 3/2. We first deal with 1. So here we shall have another enthalpy, because now we shall be having the first ionization energy, where we shall be forming the first aluminum ion. So we shall have, here we shall have formed aluminum ion, the unipositively one, gaseous, plus 3 out of 2 fluorine gas. So this one is giving us the first ionization energy, and the first ionization energy is positive 577. Let me extend this a bit. So this one will give us our second ionization energy, where we shall have aluminum dipositively charged gas plus 3 out of 2 fluorine gas. So at this rate, we shall form the third one, which we shall have as aluminum 3 gas plus 3 out of 2 fluorine gas. So here we have the second enthalpy, the second ionization energy, and it was given as plus 1820. Then here we shall have third ionization energy as plus 2740. Now, after having formed this, aluminium ion, now we are done with aluminium part. So now we are going for the fluorine. Now, they gave us bond dissociation energy of fluorine. And clearly, we defined what bond dissociation energy is. Yeah, we say that bond dissociation energy refers to that energy required to break 1 mole of a single covalent bond. But here we are breaking 3/2 moles. Yeah, so the bond dissociation energy will be 3/2 times the bond dissociation energy. So we are going to have 3/2 bond dissociation energy which was plus 158. Then after dissociating this bond, remember we form free gaseous atoms. When the bonds dissociate, or when we break the bonds, we form free gaseous atoms. So here, at this rate, we are going, after breaking this bond, we are going to form 3 fluorine gaseous atoms. So we shall have 3 fluorine gaseous atoms. And also here, remember, we have formed aluminium gaseous atoms. Then now, after this, we were given electron affinity, but it was negative. We were given electron affinity of aluminium. So, or rather of fluorine. So, and remember electron affinity, we say that it is the energy. This is the energy, if you were to remember very well the definition that we gave about electron affinity, we say that this is when 1 mole of an electron is added to a substance, isn't it? Yeah, we called it electron affinity, and we defined it as that energy given out when 1 mole of electron combines with 1 mole of gaseous atoms. But remember, these are 3 moles of gaseous atoms, so the enthalpy of electron affinity would be 3 times for 1 atom, because what they have given us is for 1 atom, implying that I will have 3 times the enthalpy of electron affinity, which was the first. So it will be 3 into negative 348. So at this rate, we form a unipositively. So it is going to be aluminium 3 plus gas, of course, then plus 3, since we are forming 3 gaseous atoms. And this one will give us directly what we call aluminium fluoride. So these 2 gaseous atoms can combine to form a crystal lattice, and that is what we call the lattice energy. So we shall have the H lattice. That is what we call the energy level diagram. Very, very, very interesting. So by Hess's law, we are going to get the enthalpy of formation of aluminium fluoride by summing up everything that we've gotten them. By summing up everything. So our enthalpy of formation would be equaling to the first atomization, the atomization energy, the first electron affinity plus second electron affinity plus third electron affinity plus 3/2 bond dissociation energy plus 3 of electron affinity plus the H lattice. All that will give us electron affinity. So allow me remove this and calculate the rest of the part. So we are going to say that from Hess's law, enthalpy of formation of aluminum fluoride is going to be equal to enthalpy of atomization plus first ionization energy plus second ionization energy plus third ionization energy plus 3/2 bond dissociation energy plus 3 times electron affinity plus lattice energy. So when you substituting, this was given as -1301 equals 314 plus 577 plus 1820 plus 2740 plus 3 out of 2 of positive 158, then plus 3 times -348 plus lattice energy. So correct like terms together, bring everything this side. And I want to see if every viewer will get lattice energy as -5945 kilojoules per mole. Yeah, let's see if everyone will get this. Then the last part, they say that if the hydration energies of aluminum ions and fluoride ions are 4690 and 364 kilojoules per mole respectively, calculate the enthalpy of solution. Now, for that part, you need to first know how aluminum fluoride behaves, since they want enthalpy of solution of aluminum fluoride. So we are going to have it in aqueous state, but when it dissociates, it will form that and 3 fluoride ions. So we need first they give us enthalpy of hydration of these ions, yeah? So enthalpy of hydration of aluminum fluoride is given by, shall have enthalpy of hydration of aluminum ion plus 3 times enthalpy of hydration of fluoride ion. So this is going to be, they gave this as -4690. And even if they had given any hydration energy as negative, for you have to consider, rather as positive, for you have to consider them negative. Because we say that hydration involves evolution of heat. Hydration of the ions involves evolution of heat. So they must be negative. And this will give you -5782 kilojoules per mole. So after getting this enthalpy of hydration, then now you come and say that enthalpy of solution is going to be equal to lattice energy. We are getting enthalpy of formation of aluminum fluoride is going to be equaling to lattice energy of aluminum fluoride, of course, plus enthalpy of hydration of aluminium fluoride. Much as we've gotten our lattice energy as negative, but we use the one of dissociation, so which must be taken positive. So the enthalpy of lattice is going to be taken positive. So the H solution, enthalpy of solution, is going to be going to positive 5945 plus, this one must be negative, negative 5782. And this will end up becoming positive 163 kilojoules per mole. So that is the deal behind it. I'm going to do one more question and then I go to Von Haber cycles. I'm going to do one more, then I can take us to Von Haber cycles. So we are going to be given the thermochemical data. We're going to be given the thermochemical data, and they give us enthalpy of formation. I'm going to give them in brief form. Enthalpy of formation of calcium oxide was given as negative 635. Then they gave bond dissociation energy of oxygen, and it was given as positive 498. Everything is in kilojoules per mole. Then first electron affinity of oxygen. First electron affinity of oxygen, and was given as negative 140.9. Then we have second electron affinity of oxygen as positive 770. In inorganic chemistry, in our discussion of trends, we shall see the reason as to why the first electron affinity of oxygen is exothermic, while the second electron affinity of oxygen is endothermic. This one, we are going to discuss it in inorganic chemistry in our lessons of discussing the trends. Then we have the atomization energy of oxygen as positive 193. Then we have first ionization energy it was atomization energy of calcium as that. Then first electron affinity of calcium is given as positive 589.8 kilojoules per mole. Then we have second ionization energy of calcium, and it was given as positive 1145.5 kilojoules per mole. And the requirement is calculate the lattice energy. They want us to calculate, all these ones are in kilojoules per mole, but they want us to calculate the lattice energy. Now, I'm going to sketch my energy level diagram here, and then we see how we go about it, yeah? Here we shall have our potential energy. You have to write in full words, potential energy in kilojoules per mole. And we shall have 0, for we have some negative values. And here we shall have the enthalpy of formation of calcium oxide. And this is was given as negative 635. Then after this, we are given the atomization energy. So we write the equation calcium here. It is a solid, and we are going to add a half oxygen to balance the equation to get calcium oxide, yeah? Gas. Now this will give us calcium as a gaseous atom after it has undergone atomization, then plus a half oxygen. So the energy change here is the enthalpy of atomization, and it was given as positive 193. After you formed an atom of calcium, then now this calcium gaseous atom will undergo first ionization energy. So we shall be having the first ionization energy, and it was given as positive 589.8, yeah? Then from here, still we are going to have a second ionization energy, whereby here, this unipositively charged gaseous ion will be giving us a dipositively plus a half oxygen. So here, the enthalpy of second ionization energy was given as positive 1145.5. So after we have formed these, after we have formed the gaseous atoms, yeah, now we shall have a case whereby now it is the oxygen that will undergo the bond dissociation energy. So the bond dissociation energy, that is where we form free gaseous atoms of oxygen, yeah? So we are going to have, for the case of this oxygen, bond dissociation energy to be converted to a gaseous atom. So we shall add this side a calcium gaseous ion, yeah? And here, it means that for us to get that, we shall have a half. We have BDE, and it will be a half bond dissociation energy because a half moles of oxygen are being converted to free gaseous atom. So it will be a half of positive 498. After we have formed the gaseous atom of oxygen, we have here this gaseous atom is going to have, because now this gaseous atom undergoes the first ionization energy, and the first ionization energy is negative, while the second ionization energy is positive. So at this point here, we shall have the oxygen gaseous atom undergoing first electron affinity. So we shall have the enthalpy of first electron affinity, and it is going to be negative 1409, yeah? Negative 140.9 as given here. Then this one, to form this, it is where we had our calcium, basically our calcium and the uninegatively charged gaseous ion that has been formed. Then now we also have the second electron affinity, so you have to point upwards again. So the second electron affinity is where we shall have the formation of a dinegatively charged gaseous ion. So we shall also have the calcium gaseous ion. And here we have the enthalpy of the second electron affinity, which is positive 770. I told you an explanation as to why it is positive in organic chemistry will give us a very good idea. So here we shall have the enthalpy of lattice. Good. So we can use the Hess's law to get lattice energy, because that is what is needed. We need this lattice energy. So by using Hess's law, we know that enthalpy of formation, this is separate out of the graph, out of the energy level diagram. I told you we sketch, so you don't need a graph. So enthalpy of formation is equal to, now we start summing up. Enthalpy of atomization of aluminium plus enthalpy of first ionization energy plus enthalpy of second ionization energy plus enthalpy a half bond dissociation energy plus enthalpy first electron affinity plus enthalpy of second electron affinity, then plus lattice energy. So substitute appropriately and get me lattice energy, which you should get as negative 344 1.7 kilojoules per mole. But in case you don't get the same answer, you can comment and we see how to help. Okay, so that is it with the energy level diagrams. And now we are going to come on with Born-Haber cycle. Okay, we are going to come up with Born-Haber cycle. Wish you well.